Quote, bang, bang, bang. Maybe you've heard of or seen this energy drink around called Bang, with its crazy flavors such as unicorn and Star Blast, which aren't flavors at all, they're words. Whether you identify Star Blast as a flavor or not, it doesn't matter, because Bang comes in a can. And when something's in a can, a cylinder-like can, we can take it and optimize it. Yeah. As you just saw, diameter across the can is 7 centimeters, so we can figure that radius is 3.5 centimeters. Next, using our pink flexi rule ruler, we will find the length of the can, which turns out to be 15.8 centimeters. With those measurements done, we can get crack-a-lackin' into some math. As previously stated, the diameter of this can was 7 centimeters, as well as the length of this can being 15.8. Using what we know, we can calculate the can's surface area by putting in its radius where the radius goes and its height where its height goes. Solving this equation will give us the real steel surface area of a Bang can, which is 424.43 centimeters squared. Now that we've found the surface area, we can plug this into the secondary equation. Using our new equation, we can find that h equals 424.43 minus 2 pi r squared over 2 pi r. Now that we've found what h is equivalent to, we can plug h into our primary equation and solve to find the equation of the container, where we will eventually use calculus to find our maximum. Once you've got to the point where you're going to take the derivative, you could plug that equation into a graphing calculator or Desmos to get the dimensions that would make the volume of your shape, can, whatever it be, into the max. I'll show my graph for my can later in the video. Once you have your equation fully simplified, you can start doing the calculus, which I'm doing here. I take the derivative of this, then set it equal to 0. The 2 that everything is over can be multiplied by both sides to get rid of it, leaving us with 424.43 minus 2 pi r squared is equal to 0, but I just set them equal to each other here. After that, you can divide by 2 pi and square the whole entire thing. Once you solve for radius, and I got 4.75, you can plug that right back into your height equation to figure out height, which, as you'll see in a second, I got 9.47 centimeters. Once we're done finding the optimized dimensions for this can, we can start comparing it to the original dimensions. The original dimensions, the radius was 3.5, the height was 15.8. With the new optimized dimensions, the radius is 4.75 centimeters and the height is 9.47 centimeters. Both of these dimensions use the same amount of surface area. The optimized dimensions, as you know, optimize the amount of volume, maximizing it. Displayed now is the equation for the volume of the can. The point on top, the blue, optimized maximum, is what dimensions would make the can have the largest volume while still using the same surface area. The purple point to the left of the optimized maximum point is the dimensions that the can is using currently. The manufacturers of this product produce this current dimension because it is easiest for one's hands to grip at least partially around the can. If the radius of the can were to increase, the whole radius would increase and it would be harder to grip the can. Also, they would have to redo all of the stocking options. Everything would have to change from their machine factory to the place it's sold in stores. I do not believe the dimensions of the Bang can should change because the current dimensions allow for the consumer to wrap their whole hand around the Bang can And the increase for the maximum volume is only 10.4%, which is not a lot. So the current dimensions, in my opinion, are fine.